Welcome. My name is Randy Ellis. In this session, we'll review prerequisite material for nonlinear data analysis, and this will be linear data analysis. The main concepts for this session are labels are categorical dependent data that are provided to us. A classification is a way of predicting based on patterns that we've detected. A confusion matrix or a contingency matrix is an important way to relate our labels that are coming in and our classifications that are going out. And key concepts for a confusion matrix are sensitivity and specificity. So labels are dependent variables. So consider observation I, and we'll say it has a label. So this is a categorical variable, and there's a finite set of labels, and so it's not a continuous object, the way that, for example, a dependent variable in regression is. A categorical variable, often it will just be one of two values. It's in a certain set or it's not in a certain set. And we'll note that independent variables cannot be categorical. That's the way that we've set everything up, is that independent variables are part of observations and vectors. And we can't scale a category, so we're sort of stuck with these labels. And the point is that for new data we want to predict, and it's really not a new label, we want to predict what class new data fall in. So the implication for all of this is a label is a dependent variable, and we'll denote this dependent variable as y. Binary classification is the simplest and a very, very common way to do it. So in supervised binary classification, which is a common form of machine learning from data, you're given m data, and we'll think of these as vectors that have n real entries. And each point will have a binary label. Now, these labels will change. For this session, we'll use the labels -1 and +1. In neural networks, the labels are often 0 and 1. So we'll call a scoring function a map that goes from a vector to a real number. So for example, in principal components analysis, PCA, we had such a score, and that score was given by the dot product of our vector and the loading vector. So prediction or classification or quantization is a map. So it's a map that we'll call Q, and it goes from a real number, usually from a score, and it goes to a predicted value that corresponds to the labels. So if we're using labels of -1 and +1, our quantization will be plus or minus 1. Now what this means is for each data vector we have 2 possible labels and 2 possible predictions. So we have 4 combinations of labels and predictions. That means we have 4 contingencies. A confusion matrix is another term for a contingency table. Contingency table is a more formal term. Confusion matrix is a very common term in data analysis. And this is similar to a truth table in binary logic, and you took logic probably about a zillion years ago. A confusion matrix looks like this. The way that we will write it is that the labels are rows and the predicted classes are columns. In some documents, in some sources, these might be transposed. And we'll always write the label +1 first and the label -1 second. Again, this might vary depending on your source. So the key concepts here are, if the true label is +1 and we predict it as +1, we'll call that a true positive. If the true label is -1 and we predict a -1, we'll call that a true negative. And these mean that our classification matches the label. In these off diagonals, our classification does not match the label. Looking at this, if we predict it to be +1, but it's -1, we'll say it's positive, but it's a false positive. It's not a true positive. Likewise, if we predict -1 but it's actually +1, we'll call that a false negative. And we'll say that the sum of the true positives and the false negatives is P, so that's for positive. And then the number of false positives plus true negatives, we'll use the symbol N for negative. Now, referring to our confusion matrix, these are key terms. The sensitivity is the true positive rate. So this is the true positive number divided by the positive number. So that's a ratio, and that will vary between 0 and 1. The specificity is the true negative rate, so that's the number of true negatives divided by the total number of negatives. Again, that will be varying between 0 and 1. The accuracy is the true positives plus the true negatives divided by as many data as you have. So this also will be bounded between 0 and 1, and accuracy is a very common single number for measuring the results of your classifier. A type 1 error is a false positive. It's sometimes called a false alarm. And a type 2 error, a false negative, is also called a miss. So key concepts in classification are the accuracy of the number of predictions that match the labels. That's our true positives plus our true negatives divided by the number of data that we have. The sensitivity is the relative occurrence of true positives. The specificity is the relative occurrence of true negatives. And if we have a hyperparameter in our classifier that we can vary, what we'll discover is that sensitivity and specificity co-vary with the value of this hyperparameter.